morning. Welcome you all to this NPTEL course on electrical distribution system analysis. And today we are going to discuss on the topic titled Definition and Objective of Volt-var Control, popularly known as VVC. Now, by the definition itself, when we talk about Volt-var control, there are two things that comes to mind. One is voltage and the other is actually reactive power. So, as we all know from the fundamentals that there is a strong relationship do exist between reactive power and voltages, and probably in a distribution system it is very important to maintain the voltage at each and every bus because of actually resistive conductors. Most of the cases long radial feeders do consume lot of voltage drop and leading to uncomfortable circumstances for equipments to experience either low voltage or high voltage experiences. Now let us focus on what is VVC. Now when we talk about Volt-var control VVC, which is a critical process in electrical distribution system, focusing on managing and optimizing voltage levels and reactive power. Now imagine a radial feeder having 3 buses with a supply source of actually voltage V, and 3 different buses do experience voltage of V1, V2, V3. If you set 1 per unit at my sending end substation, probably the last bus will experience reasonably less voltage compared to the first and second bus. Now the question is, how can we make sure that the sending end supply voltage is almost closer or reasonable at each and every bus? And that is the challenge which can be addressed through this topic today. This process is fundamental to ensuring efficient operation and stability of the distribution system, directly influencing the performance and reliability of power delivery to end users. So the main objective is that each and every end user of a distribution system must receive 1 per unit of voltage as designed without fail. Now when you have actually VVC, what are the advantages we can experience? By optimizing voltage profile, VVC not only enhances service quality for end users, but also achieves critical operational goals such as significant reduction in real power losses and precise control of voltage variation. There are 2 things. Losses need to be reduced. Okay, if your voltage difference is low, naturally the losses will be low, as well as we can make sure that the voltage experienced at each and every bus is not too much variation being experienced by the end users, leading to a more efficient and reliable power distribution system. Now, if you focus on any substation, for example, let's say the LTC, that low tap changers, and when the overhead lines, as you could see, you can experience many capacitor banks, transformers, voltage regulators. They all are mainly designed to make sure that the voltage being used by the end user is as desired to 1 per unit. Now, what are the history behind Volt-var development, both in respect to research over a period of time? So starting from 1930, we had actually load controls, but considered to be not very reliable, which is a local measurement, no system level coordination, poor visibility and poor performance. But over a period of time in 1960s, the static VAR optimization, which is a popular topic as you all know, in which reactive power control has been achieved, optimal location of the capacitor banks, but which was considered to be a very costly operation. Then in the year of 1980, now we moved to centralized control, CVR not included, and few measuring points, no voltage constraints, and only one-way communication. Now in the year 2000, we move to Volt-var optimization that we are talking about today. The CVR, which has been included, coordinated, more reliable, two-way communication, and centralized as well as decentralized control. Now, 2020 considered to be a latest modern techniques are being used through control mechanisms, hierarchical based VVCs, and today we are talking about machine learning and AI based VVCs too. Now, what is exactly the main objective of Volt-var control objectives? Now, first of all, we need to improve the voltage profile of the system. Now, voltage is a fundamental parameter to evaluate the quality of electrical services. If you are experiencing a constant voltage available to you at your terminal, means your distribution system is doing a good job, fantastic job. Now, standards define the voltage limit for normal and abnormal conditions, that is emergency, after outage for a period of time. If the voltage levels are out of acceptable operating ranges, then these are the following challenges one can experience: inefficient power system operation, degraded performance of equipments, because if it is designed for, let's say, 230 volt, and if you are providing 200 or 270, naturally the equipment is going to underperform. Potential damage on equipments, that is customers may experience equipment damage, safety hazards, and possible activation of protection equipments. Now, in case of voltage profile improvement, we'll also calculate, starting from a generating point to a load point, how the voltage is being experienced. To accomplish the voltage regulation, the planning and operation design of the distribution system must consider the maximum allowed voltage drops of the selection and setting of the equipments, such as old ECs, SVRs, and SCS. The simple two-bus power system, which has been shown in figure number 1, will be considered to illustrate the voltage drop in a distribution system. Now, assume that this is my supply voltage at generating end, which is Vg, and the load end voltage, which is VL, and this is the feeder with the impedance of R plus Jx. The load quantity may be assumed as PL plus JQL. Now, the voltage difference Vg minus VL is given by the line impedance, that is R plus Jx, multiplied by the current, which is I vector. Now, which is nothing but your delta V plus J delta V. Now, if you represent the vector diagram, I can easily do this way. This is my generation voltage Vg. There is a drop, reactive component. There is a drop, resistive components, and finally I land up with VL. Or reverse, I can say VL plus the resistive drop, reactive drop, and finally I get what is Vg. So the strong relationship between Vg and VL, which has been established in the above equation, but it is certain that the load voltage and the generation voltage are not necessarily to be same. Now, the difference in voltage is going to be this term or this term. We have to make sure that delta V plus J delta V or J dou V or R plus Jx times I must be considered to be as minimum as possible. And if the term is going to be 0, theoretically assume, so then my VL is going to be Vg, which is not practically true. But because of feeder impedances, we need to have mechanisms through which VL must be very, very close to Vg. The demand current I is related to the consumed power PL plus JQL, and the voltage VL of the load given by the expression, which is I, which is my load upon voltage, that is PL minus JQL upon VL star. And from the above equation, now we had an expression which speaks about Vg minus VL, which is R plus Jx times I. If I substitute the value of I from the above equation, and then I can get one more equation which is given by RPL plus xql upon VL plus J times xpl minus RQL upon VL, which is nothing but my delta V plus J dou V. Now for a small power flow, the component in quadrature, that is dou V, is small and the voltage drop might be approximated by delta V. Now the component of the voltage drop in phase with the load voltage. Now how do we experience or how do we achieve loss reduction? Now loss reduction means probably you need to have a feeder, but you can only minimize the losses, but you cannot completely ignore it. Now electrical losses in any system component during energy delivery, electrical losses occurs in system components like lines, transformers, capacitors. These losses are a combination of power losses as well as energy losses. Now, how do we reduce energy losses? Reducing energy losses is beneficial for both utilities and customers, resulting in cost saving and improved service quality. Line loss calculations, let's see, the line or feeder losses are the difference between the supplied power SG and the consumed power SL. So S loss is nothing but the difference between SG minus SL, that is delta SR. And one can easily calculate S loss, which is Vg minus VL times I star, which is nothing but R plus Jx I star, which can further be reduced to I square R plus I square X J component. So the first one is considered to be the real power loss component, the second one is reactive power component, and we can say that P loss plus JQ loss for any distribution system. So the active power loss component, they are the part of the total power losses and can be represented as IR square plus I square times R. And the estimated energy losses one can calculate using the following formula. Energy losses over a period can be estimated in kilowatt hours using the rectangular integration method, where E loss is the total energy loss and PL loss and P loss in I plus 1th iteration are the active power losses at time I and I plus 1, and delta T is the interval between the times. So energy loss can be calculated as summation of I equal to 1 to Ni, P loss ith component, ith time interval, and P loss I plus 1th time interval upon 2 multiplied by delta T will give you the total energy. Now there are different approaches to reduce active losses. One can reduce active losses either by replacing lines with reduced resistance or by reducing the currents in the lines. Because when you say I square R, either you reduce current or you reduce resistance. This can involve physical changes to the network or the application of Volt-var control techniques to optimize the reactive component of the line current. So probably through volt, because physical conductors, replacing for a low resistance conductor is not that easy. However, the current component can be controlled through proper Volt-var control techniques. Now, there is a term known as conservation voltage reduction, popularly known as CVR. And what is CVR? CVR aims to reduce voltage levels on the network to enhance peak demand reduction and energy saving. It serves the objective of Volt-var control by focusing on energy efficiency. Now, studies have shown a demand reduction ranging from 1 to 6% due to CVR. So, with the presence of CVR, the demand reduction can reduce from 1 to 6%, making it a cost-effective energy saving strategy. You must have heard that if an air conditioner, if you operate with 1 degree Celsius higher operating point, then you must have told that the total energy consumption of the system will reduce drastically. I think we'll link this concept to CVR in due course of time. But the CVR factor is used to evaluate the effectiveness of CVR, defined as the energy saving for a 1% voltage reduction. That is the formula of CVR factor, which is given by the change in energy delta E percentage upon the delta V percentage. Means by changing the voltage by 1%, how much energy is going to be saved. Now the delta is the percentage of energy reduction and delta V is the percentage of voltage reduction. Load response to voltage changes. Now, what is the relationship between the voltages and loads? Voltage dependent loads and load dependent voltage scenarios. Now, in case of a medium voltage network, loads are modeled as voltage dependent. The active and reactive power of load can be represented by the exponential model, which is expressed as PL, which is PLN times VI upon Vn to the power Kp. So this is my real power load model and this is my reactive power load model where QLI equal to KLNI VI upon V and KQ. Means we want to emphasize that the real power and reactive power are strongly dependent on the voltage experience at the terminal point. In this equation, both PLI and QLI are the active and reactive power load power at the bus I. PLN and QLN are the nominal active and reactive power at rated voltage Vn. And Vi is the voltage at bus I, and Kp and Kq are the voltage exponents for active and reactive power respectively. Effective CVR implementation requires a cost benefit analysis and a methodology approach to estimate energy saving before its application. Accurate assessment of CVR benefits is challenging due to variable nature of loads and load components. The main technical issues outlines for CVR, which includes coordination among various Volt-var devices for reliable and optimal voltage reduction, assessment and verification of CVR effects, coordination between CVR and distributed generation, that is DGs. Now, as per the utility perspective of CVRs, utilities can benefit from peak load relief, net loss reduction, and increased social welfare. That means if I do plot a characteristic, this is my load characteristic, and this is the power demand, and possibly this is the time, and assume that we are experiencing the peak load at 7 p.m. theoretically. And the first black one, which talks about daily demand curve. And if you implement CVR, then you experience this loaded curve, which is a dotted one. That means if you're due to the CVR implementation, if your peak load reduction, so this is my peak load reduction, and that will certainly, the green strip talks about the amount of energy that is being saved. Reduced energy consumption can lead to revenue losses for utilities, necessitating incentives to compensate for this and ensure return on your investment. Means the amount of money that you spend for CVR implementation, probably that can be easily recovered through your reduction in energy consumption. So, thank you very much.